Okay, welcome back. We covered this, and a few words about model fit R square. Just a reminder, R square will always increase when more variables are added to the model, because more variables will lead to more flexibility, and a more flexible model is able to capture the variables in the data better. The book says it also in a different way, that adding another variable to the least squares equation must allow us to fit training data. Again, it's about the training data more accurately. And so this is something known. The RSE, which is defined as the square root of the residual sum of squares divided by n minus p minus 1. P plus 1 is P plus 1 are the degrees of freedom. P is the number of features. The plus 1 comes from the intercept. And it is possible that when you add predictors, that the RSE can increase slightly. Because yes, the residual sum of squares reduces, but so does n minus p minus 1, because as we add more variables, we are also increasing p. Okay, and yeah, so that's just something to remember. And here is just a geometric illustration of what it means to perform multiple regression. We have sales, and we regress it against TV and radio. For any combination of amount of advertisement made on TV and radio, there's a corresponding sales, which is the red dot, and linear regression finds a hyperplane. A plane in 3 dimensions is a plane, but in more than 2 or 3 dimensions, it's a hyperplane. A hyperplane that is as close as possible to all data points as possible. That is as close as possible to the data points. A plane that is as close as possible to the data points. And as close as possible means that the residual sum of squares, which is the sum of squares of these distances, is small. Okay. The next thing we will talk about is the difference between prediction interval and confidence interval. And the book in page 82 talks about it specifically, and I will talk about it too, but just because I like to make references to the book, that's why I'm referring it here. So in short, the prediction interval involves both the reducible error, this should be error, sorry, error that we get in the estimate of fx, and it's reducible because of 2 reasons. Either we can increase the amount of data we have, increase the sample size, or we can just have if we are using a biased model, we can use a model that is less biased or not biased, that is more flexible, so we can reduce it. But then there's also the irreducible error. The error that summarizes everything that goes into the response but cannot be explained by X. We model it as random. And even if you have the population mean, an individual data point, like if you draw a random sample, that individual data point is not going to be the same as the population mean. It will tend to be close to the population mean, but will fluctuate around it. And that's where the irreducible error comes from. The prediction interval is always wider than the confidence interval. The confidence interval only includes the reducible error, the error that stems from the reducible aspect of the statistical learning problem. And if you want to read a little bit more, just go to page 82 of the ISLR book. Okay. The next topic is how to deal with qualitative predictors, especially when they have more than 2 levels or more than 2 categories. If they have 2 categories, we can simply code one as 0 and the other one 1 and treat them as non-categorical. Here's an example. This is a binary, and we code the predictor as gender 1 and 0. If we quote it in this way, the coefficient that we are going to get associated with gender is going to take male as baseline because it's 0. So the effect that we are going to see is going to see it female in relationship to male. Now, if we want to switch that, then we should just switch the coding. And yeah. So the numbers may change, but the final interpretation doesn't change. I mean, just one versus the other one, and it's just all about which one do you take as the baseline. So if Y is the response, X is gender, when the gender is female, then the response is beta 0 plus beta 1 plus some irreducible error. But if gender is male, then the response is beta 0 plus noise. Now, the binary coding can be replaced with this coding where it's 1 and negative 1. The numbers that we're going to get for the coefficients are going to be different, but the overall interpretation will not be different. Well, let's see how the meaning of each coefficient will depend on how we code it, and it will be different. Let's look at it. If, again, this is a simple linear regression model. If gender is female, then the response is beta 0 plus beta 1 plus the irreducible error. But if gender is male, it's beta 0 minus beta 1. So the interpretation of beta 1 is different from the interpretation of beta 1 here. These two are different. But both codings are valid. This is what I have seen mostly being used. And if we have 3 categories, then for each category we have a binary variable. So we have 3 categories, 3 races: Asian, Caucasian, and African. So predictor 1 is 1 if race is Asian, 0 otherwise. Predictor 2 is 1 if Caucasian is 1, 0 otherwise. And assuming that every individual in this data set falls into Asian, Caucasian, or African, then this model, which is studying the association of yi with the 2 predictors, which are just race. These are 2 predictors, but they stand for race together. They represent race, and the meaning of the coefficients again hinges heavily on how these 2 predictors were defined. And if race is African, then the response is beta 0 plus the irreducible error. If it's Caucasian, then this coefficient is 1, this coefficient is 0, so it's beta 0 plus, sorry, this coefficient is 0, this coefficient is 1, so it's beta 0 plus beta 2, and so for Asian. So beta 1 and beta 2 are the coefficients for Asian and Caucasian gender in relationship to the baseline, which is African American, in this way of coding. So we can just switch all of these. There's it will just change the coefficients, but all I'm trying to say is that when you're dealing with categorical variables, the meaning of the estimated coefficients depends on what is the baseline. Here the baseline is African American. Here the baseline is male. So you get the idea. The next item is interaction terms. Here we have the 2 predictors, x1 and x2, and then here we are adding the interaction term. What the interaction term is doing is adjusting the way any variable is associated with the other variable depending on the second variable. So without this interaction term, the association between y and x1 can be summarized with beta 1, regardless of what x2 is. But the moment we have interaction, the relationship between y and x1, the association will depend on beta 1 and beta 3 x2. As a general rule, when we have interaction terms, we also use the effects, the main effects, because without them, the interpretation of the interaction becomes problematic. And when we are having an interaction between a qualitative and a quantitative one, we are saying that we are interested in fitting a regression model that gives us separate coefficients depending on what the qualitative variable is. So it is similar to fitting different regression models for every value of this qualitative variable. Now, you're fitting balance, you're regressing balance against income and the qualitative variable of status, student or non-student. Okay, so the response here is balance against income and status. Let's say xi2 is the income of the ith student, and xi1 is the, xi2 is the income, xi1 is the status, whether student or non-student. This can be summarized into two regression models. One for students, where for students the predictor student is 1. So you have yi plus beta 0 plus beta 1 plus beta 2 xi2, which is income, plus the irreducible noise error. So the balance and income will be linearly related with this intercept. And for non-students, xi1 is 0, so xi1 times beta 1 will be 0. The response is just the intercept plus beta 2 xi2 plus epsilon I. So again, this is linear. The slope is the same, it's just the intercepts that are different. And when intercepts are different, we are dealing with two lines that are parallel, but one of them is going to be on top of the other one. This is the difference. These two only have a difference of intercepts. So when there is interaction, the balance will depend on an intercept, the coefficient for status, the coefficient for income, and the coefficient for the interaction, plus irreducible noise. The status is student 1. Then you have beta 0 plus beta 1. You have beta 2xi2. And this term, xi1 is going to be 1. So you have beta 3xi2. So it's beta 2 plus beta 3 xi2 plus epsilon I. So it's a linear model in income for students. Now for non-students, this term is 0. This term is also 0 because xi1 is 0. So for non-students, we have yi plus beta 0 plus beta 2 xi2. Well, these intercepts are different. The slopes are also different. There is an irreducible error that's missing. Here there should be an irreducible error, but the take-home message is that when you have interaction with a qualitative variable, then it is equivalent to fitting two independent linear regression models to the data, each for one part of the data, one for category students and another one for non-students. So imagine you split the data into two pieces, one for observations which happen to be the status to be student, and another one for those which happen to be non-student, and you fit two linear regression models separately. It's as if you fit one linear regression with interaction. So if there's an interaction term between income and student, then it's as if you're fitting two lines with different intercepts and different slopes. The next topic is about adding non-linearities. This is the auto data set, mileage per gallon versus horsepower. This is a line. Then the blue one is a polynomial of degree 2 and then a polynomial of degree 5. Picking the right degree is itself a problem, an important problem, which falls into the category of model selection, and we will tackle it in future chapters. Briefly speaking, we use resampling methods such as cross-validation to select the correct, not the correct, but the pseudo-optimal level of complexity. Pseudo, I'm saying because we are using the data to estimate it, and because data is limited, therefore our estimate is going to be, we'll have errors, which is okay. Now, what is interesting is that the coefficient that you get for the second degree is significantly smaller than the coefficient you get for the first degree. Any guess why that is the case? Why is this much smaller than this one? It's because when you square it, horsepower is in the order of hundreds, like 10 to the power of 2. So when we square it, it goes to the 10 to the power of 4. So in order to account for that greater scale, the coefficient will become smaller. That is what is happening here. So in any regression problems, these are the potential problems: non-linearity of the data, correlation, and error terms. And when we say non-linearity, we mean that the residuals, which are supposed to be sort of random in a way, there should not be a discernible pattern in the residuals, especially when you plot them against the fitted values. If there is a discernible pattern, like this example, then it means that the f of x we are using might not be correct. There's something that has not been captured. And adding a non-linearity can help. This is the auto data, horsepower. This is the residuals we get if we fit a line. But if we fit a quadratic model, then the residuals will lose the discernible pattern that existed in terms of the dependency of the residuals to the fitted values. In other words, the fitted values cannot really tell us much about residuals, whereas in this case they could, which meant that there is something that could be captured, but we were unable to capture. Now, time series data present special challenges because observations in time are not independent. They are dependent. The values of today are going to be different from tomorrow, but they're not going to be significantly different. And that dependence is captured with something like correlation. Here we can see residuals that are just fluctuating more or less randomly. But then here we have residuals which tend to fluctuate in larger scale, in a sense that residuals go up and then go down and then go up and then go down, because the correlation between residuals that are nearby is higher. It's 0.9 as opposed to 0. This is something to observe, to plot when you're dealing with time series. Look at the residuals, plot the residuals, and see if there is a discernible pattern. If there is a discernible pattern in the residuals, that means that the model could have captured it but failed. Next is non-constant variance of error terms. In everything we analyzed so far, we assume that the irreducible error, the variance of the irreducible error, is sigma squared. In a way, we said it's constant. Sigma squared, it does not depend on the predictors. That can be violated in real data. Here. We have the fitted values. We have the residuals. Each circle corresponds to one data point. And as we can see, the residuals are more or less equally spread around 0. And regardless of the fitted value, they are just spread around 0. Now, the only thing that the fitted value can tell us is that the variability of the residuals increases. When we observe the residuals, the variability of the residuals, not the residual itself, the variability increases as the fitted values increase. Taking the log or sometimes the square root of the data can help us obtain residuals that are more, that the variance doesn't change with x. The variance, you see the variability is more or less constant, whereas here the variance here is much larger than here. So we like transformations which lead to residuals with more or less equal variance. Next is about detecting outliers. So we talked about non-linearity of the data, correlation of error terms, non-constant. Next is outliers, then high leverage points, and then finally co-linearity. Okay. Outliers. Here we are seeing a simple linear regression line. We see this observation 20, and we have a line, the red line is the least squares line, the dashed blue line is the line obtained after removing 20. 20 is an outlier, as we can see, because these observations are concentrated more or less around this line, and 20 is away. Another way of seeing this is by plotting the residuals or even the standardized residuals versus the fitted values. The standardized residuals are more informative because we can draw some lines saying, okay, if it's outside the -3 and 3 range, then that observation is an outlier. But the value of the scale of the residuals will depend on the scale of the data. So it's harder for us to determine what is an outlier, where to draw the line or where not. I made a mistake. Sorry. This is studentized, not standardized. Studentized residuals as opposed to residuals. So, just a refresher, what are residuals? Well, this is our model. Our observation is a linear transformation of our features plus some irreducible error. This is a vector in a product. Here's a matrix format. And this is our least squares estimate. And using that, we can make a prediction. Yi hat is a prediction, which is xi transpose beta hat. And then the residual will be yi minus yi hat, so the observation minus its prediction. Okay, so these are the residuals. So what is a studentized residual? We take the hat matrix and we look at its diagonal elements. So the diagonal elements of the hat matrix. This is what we call the hat matrix. Where does the hat matrix play a role? So the hat matrix shows up here. This is how the least square estimate looks. And if we want to know what is the prediction at the observations, we multiply it by the matrix X. So X beta hat will be X times parentheses X transpose X inverse X transpose Y, and this part, the X times X transpose X inverse X transpose, assuming this combination, the inverse exists, we call this the hat matrix. And the hat matrix transforms the observations and gives us the prediction. It can be shown that the hat matrix geometrically is a projection. So if this is Y, and these are the two columns of X. Imagine X has two columns only. I chose 2 as an example because that's the only thing we can plot. So if X has 2 columns, then when we're doing a regression, we're trying to project this Y vector onto the plane which is made out of these 2 vectors. This is Y hat, and the length of this will be the length of R. But anyway, this is extra. Okay. Take-home message is this is the hat matrix, and this is the residual sum of squares. This is our estimate of the noise variance. It's the residual sum of squares divided by n minus p. And the studentized residuals are the residuals divided by the estimated variance divided by 1 minus the diagonal elements of the hat matrix. The diagonal elements of the hat matrix will play a role in leverage. And when we get to leverage, I will come back to the studentized residuals to make sense out of this equation. Okay, so if the studentized residuals are greater than 3 or less than -3, then we can call that data point outlier. Okay. Now here we have an example where a point like 41 doesn't only look like an outlier, but it feels that it's also away from the rest of the data. It seems that 41 has an x value which is different from the rest of the data. That's different from the point 20, which had an x value which was around the same x value as the rest of the data. It only had a larger y value. Here we can see that the x value of 20 is around the x value of the rest of the data. It is easy to detect such points when the number of predictors is 1 or even 2, because when it's 2 you can still create a scatter plot and then detect a point which is away from the scatter plot. There is another way of identifying such points using a measure called leverage. And leverage, together with studentized residuals, are good tools to identify points that are either outliers or leverage points, points that significantly change, that adding them or removing them will make a significant change in the model. As you can see, 41 being there or not changes the slope from the red to the blue. So that's a change. And if you plot leverage and studentized residuals, we can identify 20 as an outlier and 41 as both an outlier, because the studentized residual is greater than 41, than 3, but also a high leverage point. Now, what does it mean to have a high leverage? Well, in order to answer that question, we need to first define what is leverage. Okay. So multiple linear regression, defined as finding the coefficients that minimize the residual sum of squares, beta hat. And how did we get this? That just as a review, this is the residual sum of squares. It's a function of this vector theta. We take the gradient. The gradient is negative 2x transpose y minus x theta. This is something that I went over in the previous lecture and the lecture before. And then we set that gradient to 0. And the theta that satisfies this equation is our least square vector. So x transpose y is x transpose x beta hat. Now, if X is a tall matrix, meaning that it has more rows than columns, and if the columns of X are linearly independent, which in other words means that X is full rank, then, as we discussed before, X transpose X is invertible. And when X transpose X is invertible, we can multiply both sides by the inverse of X transpose X. And then we get X transpose X inverse times X transpose Y is beta hat. Now, if we want to create a prediction, we multiply beta hat by X. We get X times X transpose X inverse X transpose. This is our hat matrix. And the diagonal elements play a key role in finding the studentized residuals, which allows us to find outliers. It also plays a role in finding high leverage points. Why the diagonals? Well, it all comes from this equation. Y hat is HY, meaning that Y hat 1 is H11 Y1 plus H12 Y2, so on to H1n Yn. So the prediction at the first data point is impacted by the observation at the first data point as large as H11 is. So the larger H11, the stronger impact on the prediction of the first data point from the first observation. The stronger H22, the stronger the prediction at that second data point is going to be by this second observation. So HII is a measure of how much the ith observation influences the prediction at the ith observation. And the larger that is, the more it shows that that data point is farther away from the rest of the crowd, so that the information that the rest of the crowd, the rest of the data points carry cannot be used to make a prediction at this observation. So large HII indicates that the ith observation is away from the crowd. And that's why this is called leverage statistics. HII is always between 1 over n and 1. The trace of a matrix is the sum of its diagonal elements, and the hat matrix happens to be a matrix only because of the way it is created, so that the trace is always equal to the number of predictors. So the average of the diagonal elements is always P over N. So P over N is a relatively reasonable measure for determining whether HI is exceedingly large or not. Observations with high leverage have unusual value for Xi. That was the whole point. Xi being the vector of all the ith observations. So if HII is significantly larger than P over N, then we may suspect that Xi is a high leverage point. This is how we can detect high leverage points. Okay, so the next topic is co-linearity. I think you have seen that co-linearity before, but I will cover it quickly here. Here we see that age and credit limit do not have a clear correlation, but rating and limit, they are highly correlated. And if we are fitting the credit balance using age and limit. So age and limit are two predictors which are not heavily collinear. They are almost independent, and therefore the contour plot of the residual sum of squares doesn't look tilted in a certain direction. In other words, it looks pretty balanced, because these two predictors are almost, they look independent. Now, when it comes to the coefficients we get when we fit balance onto rating and limit, because of the collinearity, meaning that rating and limit are so dependent, there are many combinations of rating and limit that may lead to a small residual sum of squares. And that's why we have this very tilted contour plots. But also, what I want to draw your attention to is the scale here. The numbers here, the difference between these numbers is from 0.16 to 0.17 to 0.18 to 0.19. While the values of the residual sum of squares changes from 21.25 to 21.8. Now here, when we are using rating and limit, if we change the residual sum of squares from 21.5 to 21.8, so we're moving from here to here, the limit suddenly range goes from positive to negative. So the range, the uncertainty that is incurred is significantly higher, and that's something you will always see whenever there is co-linearity. Then the estimated errors, standard errors, are larger, and co-linearity technically refers to the fact that X transpose X is nearly uninvertible, or it's not completely full rank. There are columns which are linearly dependent, and when that happens, then this matrix becomes nearly uninvertible, and when you try to do that inversion, then we'll end up with these contour plots which cover a larger area, leading to wide confidence intervals. Now the next topic will be k-nearest neighbors and some examples. I will pause here and we'll leave this for the next lecture.